Okay, good morning students. We are doing Digi class now. In Digi class we are doing listening and seeing the chapter number magnetic effects of electric current. Okay, हम इसे देखेंगे और सुनेंगे अच्छे से और इसके बाद मैं आपको भी एक्सप्लेन भी करूँगी साथ साथ कि इसमें क्या हो रहा है और आपको नहीं समझ में आएगा तो कोई भी आप उठ के मेरे से पूछ सकते हैं. ठीक है. लेट्स सी मैग्नेटिक इफेक्ट्स ऑफ इलेक्ट्रिक करंट. Magnetic fields and field lines. Magnetic field and field lines. Okay, magnetic field and field lines.
Have you seen electromagnets picking up scrap metal? The magnet starts attracting metal only when it is at a certain distance from the heap. Why is the magnetic effect not felt beyond a certain distance? This happens because of the invisible field around the magnet where it displays its properties. Can you quickly recall the basic properties of a magnet?
Basic property of magnets are they have two poles, south pole or north pole.
Magnets show polarity. One side of the magnet is north-seeking and the other side is south-seeking. Unlike poles of magnets attract and like poles repel. Magnets attract magnetic material. Magnets have an area within which magnetic effects are felt. This area is known as the magnetic field. Let's perform a simple experiment using a bar magnet and a compass. Fix a sheet of white paper on a drawing board. Place a bar magnet in the center. Sprinkle iron filings uniformly around it. Tapping the board gently makes the iron filings arrange themselves in a pattern. This pattern is the result of the amount of force exerted by the magnet. The more is the force, the more are the iron filings clinging to the magnet. This is true for the areas closer to the magnet. By drawing magnetic field lines, we can see where the magnetic force is the strongest. Patterns show the relative strength of magnetic fields. Thus, we see that the strongest forces are at the poles. As you can see here, the magnetic force is strongest near the poles. Can you explain how you would draw the magnetic field lines with the help of a compass? A tedious way of tracing magnetic field lines is by tracing the pattern formed by the iron filings around the bar magnet. An accurate method of drawing magnetic field lines is by using a compass. A typical compass needle, too, is a magnet. It is suspended on a pivot needle and it comes to rest in a north-south direction of the Earth.
ये क्या है बेटा? कंपास नीडल। ठीक है, इसमें क्या है, दो पोल्स हैं, नॉर्थ पोल और साउथ पोल। ईस्ट और वेस्ट भी शो करता है, लेकिन जो इसमें मूवमेंट होती है नॉर्थ पोल की तरफ मूवमेंट करता है नीडल। ठीक है, तो हम अगर शीट पे क्या करेंगे, आयरन रखेंगे, आयरन मेटल रखेंगे और आयरन फिलिंग डालेंगे, तो फील्ड लाइंस उससे पता चल जाएगा कि कहाँ तक वो अट्रैक्शन पावर आ रही है। तो जहां तक उसकी अट्रैक्शन पावर होगी उस पे, तो वो मैग्नेटिक फील्ड लाइंस बोलेंगे। उस पे लाइंस ड्रॉ करेंगे तो वो मैग्नेटिक फील्ड लाइंस, और एरिया वही होगा जहां तक वो पावर उसकी अट्रैक्शन की होती है। ठीक है,
What will happen if you place a compass near a bar magnet?
बार मैग्नेट के पास रखने पे क्या होगा?
When you place a compass near a bar magnet, the compass needle deflects. Both being magnets, their like poles repel and unlike poles attract. The angle of deflection depends on which part of the bar magnet you are placing the compass. The magnetic field direction is the direction in which the north pole of the compass points. Alternatively, you can move the compass from the north pole of the bar magnet to the south pole, and in the process map the deflection of the compass needle. Keep the south pole of the compass pointing towards the north pole of the magnet. Plot both the points. Plot similar points from the north end of the bar magnet to the south end. Join all the points marked on the paper by a smooth curve. This is the magnetic field line. Did you notice the deflection in the compass needle? It increases as the needle is moved towards the poles. What can you conclude from this observation? Now, let us look at magnetic field lines. They emerge from the North Pole and end at the South Pole. These lines are closed lines. Inside the magnet, the direction of the field lines is from its South Pole to its North Pole. Magnetic field lines are closed curves. The relative strength of the magnetic field is more close to the magnet. The more crowded the field lines are, the stronger is the magnetic force. Will two field lines ever intersect each other?
Okay, can the two field lines cross each other? क्या एक दूसरे को क्रॉस करे? No. Let's see.
No two field lines will cross each other. If they did, then it would mean that at the point of intersection, the compass needle is pointing towards two directions. This is not possible. The magnetic field lines also show the direction of the magnetic field. How? When mapping the magnetic field, you will come across points where the compass needle does not point in any particular direction. This indicates that there is no net magnetic field at that point. Such a point is called neutral point or the null point.
Okay, click the correct answer of the following questions about magnetic fields and magnetic field lines. What is the area within which magnetic field, which magnetic effects are most felt known as? बताइए बेटा, what is the area within which magnetic effects are most felt known as? कौन सा होता है वो? Magnetic field. Let's see. Magnetic field. Very good. Next. Where on a magnet do you observe its strongest force? Strongest force कहाँ पे होती है magnet की? Poles पे. Okay. Next. What is the shape of magnetic field lines? Curve. Next. From which pole does the field lines emerge? From the north. Okay. What is the point where there is no net magnetic fields called? Neutral point. जहाँ पे कोई भी magnetic field line show off नहीं होता. Okay. Unlike pole of magnet attract and like poles repulse. All magnets have a north seeking pole and south seeking pole. Magnet and electromagnets have an area within which magnetic effects are felt. This area is called magnetic field. Properties. The magnetic field lines appear as curved. Magnetic field lines emerge from the north to emerge from south pole. Inside the magnet, the field lines run from the south pole to the north pole. Crowded field lines indicate stronger magnetic fields. The point where the magnetic field is absent is called neutral or a null point. Magnetic field lines cannot cross each other. Okay. Next time, magnetic effects of electric current.
If you place a magnetic compass near a bar magnet, you will notice a deflection of the needle. Do you know why the needle deflects? The needle is deflected due to the magnetic field created by the bar magnet. You will see a similar deflection in a compass placed near a live wire. Why? Is there a magnet inside the wire? No. Does the wire create a magnetic field? Let us explore. Hans Christian Ørsted made the same observation in 1820. He found that the compass needle deflected when it was placed below or above a wire conducting current. He concluded that the current had produced a magnetic field similar to that around a bar magnet. There should be a relationship between electric current and magnetic field. His research later helped in designing various devices such as an electromagnet, an electric motor, a radio, and a TV. When an electric current passes through a conductor, it produces a magnetic field. He found that the direction of deflection depended on the direction of current. We have honored Ørsted by giving his name to the unit of magnetic field.
Fill in the blanks. The magnetic needle deflects in dash direction when a compass is placed below and above the carrying current. अपोजिट डायरेक्शन. अभी आप बोल रहे थे ना, वही चीज़ है. देखो अपोजिट डायरेक्शन में मैंने बोला था ना, अपोजिट डायरेक्शन में मूवमेंट होती है सर्कुलर में, ऊपर नीचे.
Different observations were made when the wire was placed above and below the magnetic needle. In each case, the deflections were observed in different directions when the direction of the current was reversed. The current flowing towards the north in a conductor placed over a magnetic needle deflects its north pole towards the west. Current flowing towards the south in a conductor placed over a magnetic needle deflects its north pole towards the east. Current flowing towards the north in a conductor placed below a magnetic needle deflects its north pole towards the east. Current flowing towards the south in a conductor placed below a magnetic needle deflects its north pole towards the west. The snow rule helps us to remember the direction of the magnetic field produced by an electric current. Snow, S and N, represent the direction of current, south to north. O represents the location of the current-carrying conductor over the magnetic needle. W represents the deflection of the magnetic needle towards the west.
Fill up the columns with suitable direction: north, east, west, south. Above the live wire or toward the live wire. Deflection है इसकी देखना सारी. Above the live wire or toward the north, east. Let's see. Ampere swimming rule.
Ampere used an analogy of a swimmer to explain the deflection of the magnetic needle. It is called Ampere's swimming rule. He assumed a swimmer taking the place of the magnetic needle and his head as the north pole of the needle. Let's imagine a wire over the swimmer above the water level. Watch the deflection of the needle and the swimmer's head. When he swims north along the direction of the current, his head, representing the north pole of the magnetic needle, tilts towards his left hand. Ampere was able to explain all the four directions of deflection of the needle with the swimmer's analogy. Ampere's swimming rule is also referred to as the snow rule.
एम्पियर स्विमिंग रूल्स के अकॉर्डिंग जो है उसका डायरेक्शन क्या जाएगी? ठीक है, सी डायरेक्शन. All magnetic field is set up perpendicular to the electric current. The state of a magnetic field depend on current. The state of magnetic field is inversely proportional to the lines. Magnetic effects of current. As first observation, snow rules, deflections of magnetic needle और एम्पियर स्विमिंग रूल्स से इसके मैग्नेटिक इफेक्ट्स ऑफ करंट पता चलते हैं. मैग्नेटिक फील्ड ड्यू टू करंट कैरिंग कंडक्टर. आप कह रहे थे ना करंट कैरिंग कंडक्टर में. क्या हुआ?
This is Earth's magnetic north. Oh, can you see the compass? Let's put the table lamp on. Ah, now that's better. But wait, what's happened to the compass needle? It's showing a deflection now. Was this caused by the table lamp being put on? See there? Each time the lamp is put on, the compass needle deflects. Why do you think the compass needle deflects each time the table lamp is put on?
कंपास नीडल में डिफ्लेक्शन क्यों होता है?
When the lamp is put on, this wire begins to behave like a magnet because of the magnetic effect of electricity. This causes the compass needle to deflect. If this wire behaves like a magnet, then should it not have magnetic poles and a magnetic field? Just like a normal magnet. Let's find out. By mapping the magnetic field lines around a straight conductor similar to this wire. First, let us insert this straight conductor through this cardboard sheet. Now, let us connect the conductor to a simple circuit consisting of a switch, a rheostat, ammeter, and a battery. The top end of the conductor is connected to the positive terminal of the battery. Let us sprinkle some iron filings on the cardboard and see what happens. Nothing happens right now because the circuit is off. Let us switch on the circuit and tap the cardboard sheet a few times. You can see the iron filings arrange into concentric circles around the straight conductor. What can we infer from this? On tapping the cardboard sheet, the iron filings arrange to form concentric circles. These circles visually depict the magnetic field created by the straight conductor. This is similar to what happens in the case of a bar magnet, when iron filings form a pattern around it. This indicates that the straight conductor is creating a magnetic field around it. Do these field lines have a direction?
बेटा आप लोग क्या करना, एक कोई भी इस तरीके से मोटी वायर लेके आना, हम एक्सपेरिमेंट को करेंगे इसको, ठीक है। आयरन फिलिंग्स वगैरह बाकी चीज़ें हमारे पास लैब में हैं, तो हम इसको करेंगे। वायर नहीं है, वायर आप लेके आना, ठीक है। सबके पास मिल जाएगा, घरों में एक्स्ट्रा तार पड़ी होती है ना, उसको थोड़ा सा करके आयरन उसके ऊपर, सॉरी रबड़ वाली जो उसके ऊपर होती है उसको हटाओगे तो उसके अंदर से निकल जाएगा। कोई भी, ठीक है, आप में से कोई भी लेके आना, इसको हम करेंगे लैब में।
The field lines caused by a straight conductor have a direction. Let us verify this with the help of a compass. Observe the deflection. The north pole of the compass needle shows the direction of the field lines. The current flow is being reversed. The bottom end of the conductor is now connected to the positive terminal. What will happen to the deflection if the current flow is reversed?
करंट फ्लो अगर रिवर्स हो जाएगा, उसी डायरेक्शन में फ्लो नहीं होके दूसरे डायरेक्शन में फ्लो होगा, तो क्या होगा बेटा? देखिए,
The deflection of the compass also reverses, indicating that the direction of the magnetic field lines has changed. Can you think of a simple way of finding out the direction of the magnetic field lines if you know the direction of the current flow?
is there a simple way of finding out the directions of magnetic field lines? Right hand thumb rule.
If you were to position your right hand in front of the straight conductor in such a way that your thumb points in the direction of the flow of current, then the direction in which your fingers curl is the direction of the field lines. Now, if you reverse the flow of current, you should be pointing your thumb in this direction. The direction in which your fingers now curl indicates the new direction for your field lines. This is known as the right-hand thumb rule. So far, we had kept the amount of current flowing constant. What will happen if the amount of current flowing is changed?
What would happen if amount of current flowing is changed? करंट चेंज होगा तो क्या होगा बताओ? मैग्नेटिक फील्ड लाइन भी तो चेंज करेंगे उसके अकॉर्डिंग.
Let us now keep the position of the compass fixed over here, so that the distance of the compass from the conductor is constant. Switch on the circuit. The compass needle deflects. Adjust the rheostat to reduce the amount of current. The compass needle shows lesser deflection now than before. So, the strength of the magnetic field decreases when the current decreases, and vice versa. What will happen if the compass is moved nearer to the straight conductor?
स्टेट कंडक्टर में क्या होगा? अच्छा, जो अभी इंस्ट्रूमेंट दिखाया था इसमें देखिए, वो इंस्ट्रूमेंट किस चीज़ का होता है? उससे करंट फ्लो कितना करना है, कम है, ज़्यादा है, वो शो ऑफ होता है. ठीक है, रो स्टेट से.
Observe the deflection on the compass. Look at the deflection now, when the compass has been moved closer to the conductor. So, the magnetic field is stronger closer to the conductor. Let us quickly summarize the important points about the magnetic field of a current-carrying conductor.
स्टेट कंडक्टर में मैग्नेटिक फील्ड्स लाइंस कैसे होंगे? रिलेटेड टू मैग्नेटिक फील्ड लाइंस एंड डायरेक्शन. नोट पोल ऑफ कंपास शोज डायरेक्शन और रिवर्स करंट फ्लो causes reverse deflections of the compass needle. Right hand thumb rule. The direction of fingers rules is the deflections of lines. Relation of magnetic field lines and current. Lower available resistance, more current or more deflection. Higher available resistance, less current, less deflection. और कॉन्क्लूशंस क्या आता है इससे? मैग्नीट्यूड ऑफ द मैग्नेटिक फील्ड इंक्रीज एज द करंट इंक्रीज एज वाइस वर्सा। करंट इंक्रीज करते जाएंगे तो डिफ्लेक्शन उसके अकॉर्डिंग चेंज होती जाएगी और कम करते जाएंगे तो कम होती जाएगी। रिलेशंस ऑफ मैग्नेटिक फील्ड लाइन्स एंड डिस्टेंस। Constant available resistance means no change in the current flow amount. Closer the compass to the conductor, greater the deflection. Further the compass from the conductor, the lesser the deflection. Conclusion क्या निकलता है? Magnetic fields decreases as distance from the conductor increase. Electromagnet देखते हैं. Let's see electromagnet.
We can hardly imagine daily life without electricity. Do you know how current is generated from this hydroelectric power station? Ørsted's discovery showed that we can produce a magnetic field via an electric current. What will happen when a bar magnet is moved inside a copper coil with several turns? In 1831, Faraday found that a moving magnet inside a coil can generate electric current. It allows us to convert mechanical energy into electricity. Faraday made a solenoid of a large number of turns of copper wire. And connected the ends of the wire to a galvanometer. There is a deflection towards the right in the galvanometer when the bar magnet is inserted into the coil. There is a deflection in the galvanometer towards the left when the bar magnet is removed from the coil. No current is induced when the magnet is at rest near the coil. EMF is induced only when there is relative movement between the magnetic flux and the conductor. Faraday concluded that a current was induced in the coil owing to a change in the magnetic flux passing through the solenoid. Magnetic flux is the number of magnetic lines of force. The strength of the induced current depends on the number of turns in that coil, the strength of the magnet, and the speed with which the magnet is moved. In other words, the magnitude of the induced electromotive force in a conductor depends on the rate of change of the magnetic flux linked to the conductor. When the magnet moves fast, the galvanometer shows high current. When the magnet moves slowly, the galvanometer shows lower current. The pointer in the galvanometer remains at zero when there is no current flowing through it. What will happen when we insert a south pole inside the coil? The deflection is in the opposite direction in the galvanometer, indicating a change of direction in the current. What will happen when the coil is moved and the bar magnet is left at rest? Let's keep the bar magnet stationary at one point near Q and move the coil towards it. The needle deflects toward the right. When we move the coil away from the magnet, the deflection of needle is towards the left. Lenz's law states that the direction of induced current always opposes the change producing it. Let us replace the moving magnet with a current-carrying coil with a greater number of turns. Let us connect another coil as shown here and name the current-carrying coil the primary coil and the coil connected to the galvanometer, the secondary coil. When we switch on the primary coil, we can observe a deflection in the galvanometer connected to the secondary coil. This shows a current is induced in the secondary coil. It is obvious that without a magnet, a live primary coil can induce current in the secondary coil. This phenomenon is called electromagnetic induction. Let's summarize the various situations possible for induced current. What's the direction of the current induced in all these cases? Moving a bar magnet with its north pole at the bottom towards the coil. Taking a bar magnet with its north pole at the bottom away from the coil. Moving a bar magnet with its south pole at the bottom towards the coil. Taking a bar magnet with its south pole at the bottom away from the coil. The induced current is high when the direction of motion of the coil is at right angles to the magnetic field.
Fill in the blanks. The dash is that coil. The dash of the magnet, the dash with which the magnet is moved. Now, देखें let's see. Number of turns. सेकेंड में है द स्ट्रेंथ ऑफ द मैग्नेट और थर्ड में Fleming's right hand rule.
In order to discover the direction of an induced current, we can follow Fleming's right hand rule. Stretch the thumb, forefinger and middle finger of the right hand so that they are perpendicular to each other. The forefinger indicates the direction of the magnetic field. The thumb shows the direction of the motion. The middle finger shows the direction of the induced current. Fleming's right-hand rule is also called the Dynamo Rule.
बताओ ऊपर क्या शो करता है मोशन करंट और मैग्नेटिक फील्ड लाइंस करंट नीचे और मैग्नेटिक फील्ड लाइंस इस डायरेक्शन में ये मैग्नेटिक फील्ड लाइंस है ठीक है moment of coil, moment of magnet और passing current in another coil. ओके बेटा इसी के साथ हमारी इस लेसन की डीजी क्लास खत्म होती है. अब हम इस लेसन से रिलेटेड एक्सपेरिमेंट्स करके देखेंगे. ठीक है. सो बाय ऑल ऑफ यू स्टूडेंट्स.